This is SpaceTime, Series 21, Episode 56. Coming up on SpaceTime. Cosmic ray neutrinos traced back to their source for the first time. Black beauty expands the window for when life could have existed on Mars. And 2 undetected asteroids speed past the Earth. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has identified a distant supermassive black hole called a blazar that's the source of mysterious high-energy cosmic ray neutrinos bombarding the Earth. The findings, reported in the journal Science, the Astrophysical Journal, and on the pre-press physics website archive.org, have helped solve a 100-year-old mystery about the origins of some of these extremely highly energetic particles. For decades, astronomers have sought to detect high-energy cosmic rays in order to better understand how these ghostly subatomic particles are generated with energies thousands to millions of times greater than those attained in particle accelerators here on Earth. Cosmic rays are high-energy particles, 99% of which are ionized atomic nuclei stripped of their electron shells, with the remaining 1% comprising solitary electrons. Around 90% of the stripped atomic nuclei are simple protons or hydrogen nuclei, a further 9% are alpha particles identical to helium nuclei, and about 1% are the nuclei of heavier elements. Cosmic rays can also be made up of stable particles of antimatter, things such as positrons and antiprotons. However, because cosmic rays are electrically charged, their paths through the cosmos are influenced, twisted and deflected by the powerful magnetic fields which bathe the space they pass through. Now, what all that means is that they don't travel in straight lines, and so their origins are really hard to identify. Luckily, some of the powerful cosmic accelerators which produce cosmic rays also emit neutrinos, which are uncharged and so unaffected by even the most powerful magnetic fields. And because neutrinos rarely interact with other matter and have almost no mass, these ghostly particles travel virtually undisturbed from their cosmic accelerators, giving scientists an almost direct pointer to their source. Crucially, the presence of neutrinos also differentiates between 2 types of gamma-ray sources. Those that accelerate only cosmic ray electrons, which don't produce neutrinos, and those that accelerate cosmic ray protons, which do. Neutrinos are elementary subatomic particles generated through radioactive decay in stars, in supernovae, in nuclear explosions, particle accelerators, and atomic reactors. The neutrino is so named because it's electrically neutral, and because its rest mass is so small it was long thought to be zero. They're the most common form of matter in the universe, and next to photons, the most common particle. They're capable of being accelerated to almost the speed of light. Neutrinos come in 3 known types, known as flavors. There are electron neutrinos, muon neutrinos, and tau neutrinos. Even more confusing, neutrinos oscillate between these flavors. For example, an electron neutrino produced through a beta decay reaction may end up interacting with a distant detector as a muon or tau neutrino. Although they have no electric charge, neutrinos do have their own corresponding antimatter counterparts, identified by their opposite chirality or handedness. Neutrinos only interact with other matter through gravity and the weak nuclear force. In fact, they're so weakly interactive that several trillion of them pass through you every second without you even noticing them. On September the 22nd, 2017, a neutrino was detected at Antarctica's Ice Cube Observatory at the South Pole. Constructed at the Amundsen-Scott South Pole Station, IceCube uses more than 5,000 photomultiplier detectors, arranged in a grid covering an area of over a cubic kilometre, and buried up to 2.5 kilometres into pristine ice. Although they're extremely weakly interactive, every now and then, just by chance, a neutrino particle will collide with a water molecule in the detector, in the process emitting a secondary charged particle, which in turn produces a sudden burst of blue Cherenkov radiation, which the detector will pick up. And because the charged particle and the light it creates stay essentially true to the neutrino's original direction, they give scientists a path to follow. The neutrino detected on September the 22nd had an energy of something like 300 trillion electron volts, and a trajectory pointing back to a small patch of sky in the constellation Orion. IceCube scientists quickly informed astronomers around the world, resulting in some 20 ground and space-based observatories turning their multitude of dishes and mirrors towards the source to try and identify it. They determined that the neutrino originated from a point in the sky about 3.7 billion light-years away, which is home to a giant elliptical galaxy with an actively feeding supermassive black hole known as a blazar at its core. The blazar, designated TSX 0506+056, is a type of quasar, shooting out relativistic jets of ionized matter perpendicular to its accretion disk as it actively feeds on material passing too close. Astronomers usually use the term blazar to indicate that the active galactic nuclei is producing beams of higher density and much more powerful bursts, usually in the form of gamma rays, than a typical quasar. This is the first time a high-energy neutrino cosmic ray has been traced back to its point of origin. One of the study's authors, Associate Professor Gary Hill from the University of Adelaide, who's a member of the IceCube collaboration, says neutrinos at these very high energies are formed after cosmic ray particles are accelerated and interact with other particles. So, what was found is not only the first evidence of the neutrino source, but also evidence that this galaxy is a cosmic ray accelerator.
We've been observing astrophysical neutrinos for about 10 years now, back in our data. And so they have to come from somewhere in the universe. And until recently, we didn't really know what objects made these astrophysical neutrinos. And so what's happened here is we've set up a system where if we get interesting events come to our detector, we'll send alerts off to the rest of the astronomical community, and they can go and have a look with their own telescopes. So what has happened here is that we've seen an interesting neutrino last September, and so an alert message has been issued to other telescopes. And these other telescopes have gone and looked, and they've seen very high energy gamma rays, and they're able to tell that they come from this blazar galaxy, which in particular, this one is something like 4 billion light years from Earth.
Right, so a blazar is a particularly active quasar that has a lot of energy in it that's active.
Yeah, so an active galaxy has some supermassive black hole in its centre, and there's a lot of matter accreting into the black hole. As the matter falls into the black hole, there's gravitational potential energy gets released, and that causes jets of particles to shoot out from the centre of the galaxy. And when those jets are pointed straight at Earth, that's what we categorise as a blazar.
As well as the jets, there are also ionized particles coming out as well. Protons and atomic nuclei and electrons and even antiprotons and positrons, things like that. The problem is these things are all charged. And so as they travel through space, they're affected by all the magnetic fields which bathe space between the source and the Earth. So consequently, we can't really work out where these things are coming from normally.
Yeah, that's correct. So unless you're at extreme high energy, the charged particles will get deflected in magnetic fields. And so certainly from a galaxy that far away, the cosmic particles, the charged particles that you've mentioned being accelerated, will get deflected even slightly in magnetic fields, and they'll take a longer time to get to Earth than a neutral particle will that travels in a straight line. And so the thing about these observations is that we've seen neutrinos and gamma rays. Gamma rays, of course, are massless, and neutrinos are close to massless, which have no charge. And so they've travelled in straight lines to the Earth and are able to pinpoint them back to the source. Now, the neutrinos and the gamma rays, we believe, are made when those other charged particles, like the protons, have been accelerated. And as those accelerating particles are escaping from the environment there, they interact with gas and other photons, which actually makes the neutrinos and gammas. So the neutrinos and gamma rays are the sort of the secondary particles coming from those cosmic rays. And it's knowing that the neutrinos are coming from that object is the clear tracer that they must be accelerating the charged particles, like you mentioned.
And then they travel through space 3.7 billion years in this case, and they eventually hit the IceCube neutrino detector at the South Pole.
Yeah, that's right. So these particles, the neutrinos, have travelled this long distance, and so one of them has just come under the horizon into the ice at the pole and has turned into a muon particle, and that muon has actually been detected in the IceCube detector. The gamma rays were detected by two observatories. The Fermi-Lap detector is in orbit around the Earth, and so that detected high gamma ray activity from this source at the same time in the same direction. And the MAGIC telescope is a ground-based gamma ray observatory, which actually detects very high-energy gamma rays when they interact and make showers of particles in the atmosphere. And that was turned onto the source as well and pointed at it and observed for some time and observed very high-energy gamma rays. So together, seeing the neutrino come from the galaxy and the gamma rays come from there tells us that it must be an acceleration site for cosmic rays.
IceCube's an incredible facility, isn't it?
Oh, it is. It's been in the works for nearly 3 decades now. So, I mean, the first idea for this was in the very late 80s and early 90s, and the first instrumentation was put in the ice at the South Pole, I think in around 1991. There was some test instrumentation put in the ice, and then one of the early Amanda detectors was built in the ice, and then the second Amanda detector was built in from 1995 through to 2000. And I actually worked on that one. I spent a winter at the South Pole after having constructed some of the Amanda detector, and then I sort of babysat it through a winter. And then I worked on the Ice Cube detector, which was approved in around the year 2000 or a bit after that. And construction started in 2005, and over 7 summer seasons, we deployed over 5,000 sensitive optical detectors into the ice, which instruments an entire cubic kilometre of the ice cap.
This is pristine ice that you, melted into?
Yes, that's correct. Yeah, so in order to get down to the depths we need to do, we use the hot water drill. So basically it's just very simple. You get off-the-shelf car wash heaters, and you use those to heat the water up, and you've got a large pumping facility and a big hose reel that has a hose on it that's about 2.5 kilometres long in one section of hose. And you basically just, like you'd use a garden hose to bore down into the mud in your back garden, you can use this big hose and shoot out hot water and bore your way down into the ice. And so it takes about 48 hours to bore the way down to about 2,500 metres and to bring the hose back out. And then so you're sitting there with this melted column of water, which is about 60 centimetres across. Then you have something like 36 hours or so to deploy the string in. So the string deployment would take anywhere from 5 to 10 hours to attach those 60 modules per string and then lower them safely down to that depth. We did that 86 times over 7 seasons to complete the Ice Cube detector.
The neutrino then slams into what? Some of the water molecules around this detector?
Yeah, it depends a little bit on where it's coming from. If the neutrino is coming directly horizontal through the ice cap, it'll hit one of the protons in the ice. And when it interacts with the proton, the neutrino then becomes visible by turning into a muon. Particles come from even right through the Earth. And so what might happen there is your neutrino might make it almost all the way through the Earth, and even many kilometres outside the detector. When it's still in the rock, you'll interact with a proton or a neutron in the rock, again turn into a muon particle, which continues on its way up through the rock, eventually passes through the ice and then gets detected in the detector.
And it sort of hits one of these molecules, and then that molecule gives off a bit of Cherenkov radiation.
Yeah, so what happens is the neutrino interacts with one of the protons, which creates the muon. And so the muon propagates along through the ice. And what the muon is doing as it moves through the ice is it's subtly stimulating the ice around it as it goes through and imparting a little bit of energy to those molecules, which then re-radiate that light as Cherenkov light. So Cherenkov light is what you get when the particle moves faster than the speed of light in the medium. So the particles are travelling at close to the speed of light, but the actual photons propagate at less than the speed of light because of the refractive index of the ice. And so what you're actually seeing is something analogous to seeing a shock wave from a supersonic jet going by. We're essentially looking for a shock wave emitted from a high-speed particle moving faster than the speed of light in the medium.
That's Associate Professor Gary Hill from the University of Adelaide. And this is SpaceTime. I'm Stuart Gary. A new study of a Martian meteorite indicates the red planet probably cooled down far more rapidly than the Earth, developing a thick crust some 4.547 billion years ago, just 20 million years after the solar system's creation and around 100 million years earlier than Earth's first crustal formation. The findings, reported in the journal Nature, suggest that developing a crust quickly meant that Mars had a head start over the Earth and the other terrestrial worlds. Forming a solid crust is an important step in the formation of terrestrial worlds. A crust provides a solid surface over a molten magma interior. That solid surface means it's possible for rivers of liquid water to flow, potentially providing conditions for life to have evolved millions of years before it evolved on Earth. The formation of planetary bodies begins with the accretion of dust and gas condensing out of the protoplanetary disk surrounding a still-forming nascent star. The gas and ice giants form further out, beyond the so-called snow line, where it's cool enough to allow the more volatile chemicals, like methane and ammonia, to condense, while the terrestrial worlds form closer in, where it's warm enough for metals and silicates to condense out. Initially, these terrestrial worlds all form as molten magma oceans. Over the next 100 million years or so, heavier metallic elements sink towards the centre, forming a core, while lighter silicates float to the surface, where they eventually cool down, start to crystallise and solidify, and create a crust. The new research is based on a study of samples of a 319.8 gram ancient Martian meteorite simply known as Black Beauty. Black Beauty was discovered in the Sahara Desert in 2011. What makes it special is that it contains small pieces of crust from ancient Mars. More precisely, Black Beauty contains zircon crystals, which act as tiny geological time capsules, providing a snapshot of the environment in which the crystal formed. They're also very robust and ideally suited to provide absolute ages. Consequently, the zircon crystals in Black Beauty can be used to establish a temporal framework to understand the formation history of the Martian crust. Scientists from the University of Copenhagen analysed elemental isotopes in 7 zircon crystals which they obtained from the Black Beauty meteorite. Isotopes are forms of an element having the same number of protons but different numbers of neutrons, hence different masses. And some isotopes are highly unstable, radioactively decaying into more stable elements at known rates called half-lives. The authors studied the radioactive decay of uranium-235 and 238 into lead-207 and 206, dating Black Beauty zircons to around 4.476 billion years. Crucially, the zircons in the Black Beauty meteorite also contained high concentrations of the element hafnium. But it turns out they weren't as high as they should have been. By studying the radioactive decay of lutetium-176 into hafnium-176, the authors were able to determine that Mars's original magma crust must have solidified around 4.547 billion years ago. That's 100 million years before the earliest zircons were created in Black Beauty. One of the study's authors, Professor Martin Bizzarro from the University of Copenhagen, says the Black Beauty meteorite expands the window when life could have existed on Mars. He says it means Mars got an early start compared to the Earth, where solid crust wasn't formed until at least 100 million years later. However, it's worth pointing out that it required a lot of courage for Bizzarro and colleagues to carry out their work. You see, the Black Beauty meteorite is so highly valued. Samples of it are priced at $10,000 a gram, and the authors needed some 44 grams of the meteorite to find the 7 zircon crystals they used. And it was one of those zircons which luckily turned out to be the oldest zircon ever recovered from Mars. I'm Stuart Gary. You're listening to SpaceTime. Astronomers have published the first global and topographical maps of the dwarf planet Pluto and its binary partner Charon. The findings, based on data collected by NASA's New Horizons spacecraft, are reported in the journal Icarus. Of course, until 2015, it wasn't known whether icy Pluto or Charon had mountains, valleys, or even impact craters. And so for the first time, these new maps by New Horizons scientists are revealing a rich variety of landforms on both Pluto and Charon. The topographic maps confirm that the highest known mountains on Pluto are the Tenzing Montes Range, which form along the southwestern margins of the frozen nitrogen ice sheet known as Sputnik Planitia. These steep-sided icy peaks have slopes of 40 degrees or more, rising several kilometres above the Sputnik Planitia floor. The highest peak rises approximately 6 kilometres above the base of the range. That's comparable in terms of base-to-crest heights to both Denali in Alaska and Kilimanjaro in Kenya. Pluto's mountains must be composed of hard frozen water ice in order to maintain their heights. The more volatile ices observed on Pluto, including methane and nitrogen ices, would be too weak and the mountains would collapse. The topographic maps also reveal large-scale features that aren't obvious in the global mosaic map. The ice sheet within the 1,000 kilometre wide Sputnik Planitia is on average about 2.5 kilometres deep, while the outer edge of the ice sheet lies at an even deeper 3.5 kilometres below Pluto's average elevation, the equivalent of Earth's sea level. While most of the ice sheet is relatively flat, these outer edges of Sputnik Planitia are the lowest known areas of Pluto, all features that are only evident in the stereo images and elevation maps. The topographic maps also reveal the existence of a global-scale, deeply eroded ridge and trough system more than 3,000 kilometres long, trending from north to south near the western edge of Sputnik Planitia. It's the longest known geological feature on Pluto and indicates that extensive fracturing has occurred in this distant dwarf world in the past. However, as to why such fracturing occurred only along this linear band is not well understood. On neighbouring Charon, the topographic maps reveal deep depressions near the North Pole. These are some 14 kilometres deep, deeper than the Marianas Trench on Earth. The equatorial troughs that form the boundary between the northern and southern plains of Charon also feature high relief of about 8 kilometres. The mapping of fractured northern terrains and tilted crustal blocks along this boundary could be due to cryovolcanic resurfacing, perhaps triggered by the foundering of large crustal blocks into the deep interior of Charon. These features make Charon the most rugged mid-sized icy satellites in the solar system, other than Saturn's high-contrast moon Iapetus. The rugged relief also indicates that Charon retains much of its original topography, caused by its history of fracturing and surface disruption. New Horizons was launched back on January the 19th, 2006 from the Cape Canaveral Air Force Station in Florida aboard an Atlas V rocket. The probe is the first and so far only mission to visit the 2,377 kilometre wide dwarf planet Pluto, its binary partner Charon, and their 4 moons Styx, Nix, Kerberos and Hydra. Pluto is one of the largest known bodies in the Kuiper Belt, a ring of frozen worlds, comets and icy debris circling the Sun out beyond the orbit of Neptune. The probe made history on July 14, 2015, when it flew past Pluto, swooping just 12,500 kilometres above the former planet's surface. New Horizons now getting ready for its next encounter on January 1st, 2019, when it undertakes a close flyby of the Kuiper Belt object 2014 MU69 Ultima Thule. You're listening to Space Time. I'm Stuart Gary. Planet Earth has just escaped a near miss as 2 asteroids coming from different directions sped past the planet over the weekend before anyone even knew they were there. The new revelations again highlight governments' lack of funding for real-time monitoring of space on a global scale for potentially deadly near-Earth objects, or NEOs. Although the United States funded NASA's doing a great job in the Northern Hemisphere, simple fact is, no one's looking after the skies south of the equator. Okay, so what happened over the weekend? Well, the first close encounter occurred at around 4:12 in the early morning hours of Sunday, July the 8th, Australian Eastern Standard Time. That's 1813 Greenwich Mean Time, as an asteroid now catalogued as 2018 NX skimmed some 110,730 kilometres above the central Pacific Ocean. That was followed at 1941 in the evening of July the 8th, Australian Eastern Standard Time, that's 9:41 Greenwich Mean Time, when another asteroid, this one now catalogued as 2018 NW, flew some 118,230 kilometres above the western Pacific Ocean north of Australia. The asteroids, each estimated to be up to 18 metres wide, weren't detected by scientists at the Palomar Observatory in Southern California until the following day, well after their close encounter. 2018 NW, an Apollo group asteroid, was observed travelling at a velocity of 21.3 km per second, about 5 times faster than 2018 NX, which belongs to the A10 group of asteroids. Of course, the frustrating thing about all this is that of all the possible natural disasters, volcanoes, earthquakes, storms, and asteroid impact is the one we can prevent, given enough warning. I'm Stuart Gary. This is Space Time. And time now to take a brief look at some of the other stories making news in science this week with a science report. Scientists from Edith Cowan University have developed the world's first blood test capable of detecting the deadly skin cancer melanoma in its early stages, an innovation that should save thousands of lives and save the health system millions of dollars. The blood test was trialled on 209 people, 105 of whom had melanoma, and successfully picked up early-stage melanoma in 81.5% of cases. A report in the journal Oncotarget claims it works by detecting antibodies produced by the body in response to melanoma. The authors examined some 1,627 different antibodies and identified a combination of 10 that are the most reliable in predicting the presence of the deadly cancer. The next step will be a clinical trial to validate the findings, with the test likely available for clinical use in around 3 years. Survival rates for melanoma can be between 90 and 95% if the disease is detected early. But once the cancer spreads, survival rates quickly drop to below 50%. And Australia's sun, surf and beach lifestyle means we have the highest rate of skin cancer in the world. A new study warns that many coral reefs will be unable to grow fast enough to keep up with rising sea levels caused by human-induced climate change. The findings, reported in the journal Nature, says this will leave tropical coastlines and low-lying islands exposed to increased erosion and higher risks of flooding. Scientists reached their conclusions by simply comparing the maximum upward growth rates of coral reefs with the predicted rates of sea level rise, finding that many reefs will be unable to keep pace. Genetic engineering has been revolutionised with the development of things like CRISPR-Cas9 and gene drives. However, a new study claims that gene editing with CRISPR-Cas9 may be a lot less accurate than previously thought. The findings, reported in the journal Nature Biotechnology, indicate that CRISPR-Cas9 also appears to edit DNA near the genes being targeted, as well as editing those genes themselves. The authors found sections of DNA, some of which were several thousand DNA letters long, had been deleted entirely, while others had been rearranged. The thing is, these unwanted edits could end up affecting the function of the genes they're trying to edit. The study is a blow to hopes that CRISPR could be easily harnessed to fight diseases including cancer and AIDS. Archaeologists digging through an ancient synagogue in Israel's Galilee have uncovered stunning mosaics decorating the temple's floor. The discovery by scientists with the University of North Carolina sheds new light on the life and culture in an ancient Jewish village dating back to the 5th century. The authors say the discovery is among the richest, most diverse collection of mosaics ever found in an ancient synagogue. They say it'll revolutionize science's understanding of Judaism in this period. Ancient Jewish art is often thought of as aniconic, but these mosaics are colourful and filled with figured scenes, attesting to a rich visual culture, dynamism and diversity in the late Roman and Byzantine periods. The mosaics are divided into 2 rows of panels containing figures and objects with Hebrew inscriptions, including the phrase Amen Selah, meaning Amen forever. Virtual reality is looking at playing a bigger role in enriching the lives of our elderly, allowing people confined to bed, those with limited mobility, or simply unable to get out as much as they'd like to experience some of the world's great sights and adventures from the comfort of their homes. With the details, we're joined by Alex Zaharov-Reut from IT Wire.
Samsung has done a pilot with an aged care home company called Uniting. And what they've done is to take the virtual reality headsets loaded up with content that some of the aged care residents wanted, to give them the opportunity to tick off bucket list items that they're basically now too old to be able to do in real life. And it's proven to be a great success.
So what, they get to visit the International Space Station or go skydiving or scuba diving, all from the comfort of their Zimmer frames?
That's right. Well, one of the people involved wanted to go on a spacecraft, orbit the Earth, check out the International Space Station. And this video is available online. Anybody with a Google or a Samsung VR headset should be able to get access to that footage and look around. But of course, for people in nursing homes or aged care homes who don't have access to the technology, don't necessarily even know it's aware, for them, it's really new and exciting. And this has helped actually people with dementia to be able to do something that's a lot more exciting than the everyday activities you might have in a nursing home. Some people wanted to visit their hometown from decades ago when they'd left from one country to come to Australia. Another chap wanted to visit the Canadian redwood forests, which he's never been able to visit.
It's not just the oldies who get to use it too. A lot of people are stuck at home. They don't get a chance to go out very much. This provides them an opportunity to see the bigger world.
Absolutely, and at a much cheaper price than getting on a plane without all the jet lag.
Alex Zaharov-Reut from IT Wire reporting. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download Space Time as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favourite podcast download provider. Spacetime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more Spacetime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.